Hello, everybody. I want to supplement your instructions for preparing your report for the kinetics lab. Um, in the previous video, um, number 7 was actually number 8 for your report. So I need to do number 7, and I have it printed out here. Number 7 says, plot the 1 over t comma ln k0 points using the T's and K's from runs A, D, and E. These are the 3 different temperature runs. So I want to do a little background and show you why that's important to make this plot. And it all stems from the Arrhenius equation, which shows the dependence of the rate constant K on temperature. So you know the rate constant for any rate law, like this one, is only going to be constant if the temperature is constant. Also, if you use the method of isolation, then that constant, like you saw, changes as well with a concentration that's in the majority and is pretty much constant. But anyway, typically K, the rate constant, only changes with temperature. So we have 3 different situations of temperature, but they all have the same concentration. So that's for the runs A, D, and E. They all have 20 mils of the dye and 1 mil of the bleach. So it's the same concentration, they're just different temperatures. This guy, A, is the room temperature, D was your cold run, and E was your hot run. All right, so what's this have to do with the Arrhenius equation, and how can we use that to calculate things like the activation energy? All right, so if we take a look at the Arrhenius equation, K equals A times e to the minus EA over RT, where EA is the activation energy, R is that ideal gas law constant in different units, 8.314 joules per mole Kelvin, and T is the temperature in Kelvin. We can take that form and show it that, every time you change the temperature, you get a different K. So I can put a little subscript I, and that runs through whatever 1 to infinity, as many different temperatures as you can think of. That's as many different Ks that there are. All right, well, to make this equation a little more useful as far as extracting information from experimental data, we can take the log of both sides, the natural log. So I can take the natural log of both sides of this equation. And when I do that, I can use the law of logs on this side, which says that the log of x times y equals the log of x plus the log of y. So I'm just going to split out that a factor, that a, this is an a, from the other part. So the other part, I can have the log of e to the minus EA over RT, and I know that the natural log of anything E is inverse functions, so that E gets wiped out, and minus EA drops down over R, and then the 1 over T is there, and I can run that as an index, plus the other part, ln A. So this is another form of the Arrhenius equation, and the advantage of this form is it shows you that K is an infinite point function dependent on the independent variable temperature. And so we get a form of a straight line if we plot the log of K versus 1 over temperature. So that's why this question asks you to do that. So we have those 3 different temperature points, right? And you solve for each one by plotting and then associating the slope of the line of your log of concentration versus time plot with the Ks, K, A, B, C, D, E, and F. Anyway, the 3 points that you're going to look at is the 1 over T versus ln K for the hot, cold, and room temperature. So we'll go cold, room temperature, hot, cold, room temperature, and then the hot room temperature. All right. Now, if I make a plot of this, which you're going to do, it should look something like this. So on the y-axis, you're going to have the log of K, and the x-axis, because this is just 3 points, they're x, y points. So x being 1 over temperature, and the y being the log of K. So I see that my high temperature is going to have the lowest value here. So that high temperature should be somewhere here. Then the room temperature maybe is a point here, and then the cold temperature is going to be the highest 1 over T value. So again, this point should be 1 over T hot minus ln K. That would be E. And then this point here corresponds to 1 over T room temperature, comma, ln Ka. And then this guy's the last one, which would be 1 over T cold, ln Kd. All right, so once you have that out there, then you can ask Excel to fit it to a straight line. And then you're going to ask Excel to give you the formula of this straight line. So it's going to say y equals, and then it's going to give you some number. Call that just number 1, x plus some number b, 2. And so through association with the Arrhenius equation, you'll be able to calculate the activation barrier and the pre-exponential function a. So let's rewrite that. Ln K equals minus EA over R times 1 over T plus ln A. So I see that the number that Excel gives me for the 2 value is related to A, and that slope here is related to EA. So you can see that the slope is going to be negative, and a negative cancels out a negative. So EA is going to be positive. But anyway, that number 1, which is negative, is going to equal minus EA over R. And I know what R is because it's, you can look that up, and I gave you that value back here. And so this number 1 is negative, and the 2 negatives cancel out, and I get a positive EA. So make sure that you put everything in the appropriate units, and you get an EA in either joules or kilojoules. All right, and now for A, the pre-exponential factor, then lna is going to equal that number 2 that Excel gives you. And so you can take the inverse log of each side. And then so A would equal E to the whatever that number 2 that Excel gave you in the plot. And then you can address all of the things that you need to for this. So let's just read through it again. So you made that plot of those 3 values and used the Arrhenius equation. You added a trend line and you found the slope and the intercept to find EA and A. Make sure that you have the appropriate units. Make sure that you have all the labels and the titles in your plots correct. And you take out the X and the Y and ungenericize that formula, and you put in, what you're plotting, which is the log of the K versus 1 over temperature in units of Kelvin, and then hand that in with your report. So I think that should get you guys going. And if you have any questions, I'll be around. Thanks for listening.